erosion question is not coming, but here in the design of unlined canal, this erosion is coming very much. And of course, in case of non-alluvial channel, where erosion is not that much significant, it can be significant or it becomes significant when the velocity exceeds a particular limit, and that we call as a maximum permissible velocity. So, in non-alluvial channel, our design principle is that our velocity should not exceed a maximum permissible velocity, and then of course, if it carries some sediment, which is not a regular problem of non-alluvial channel, but still if it carries some sediment, in that case the velocity also must exceed a very minimum velocity, which will not allow sedimentation if that water carries sediment or if sediment laden water come through the channel. Well, that was the discussion about non-alluvial channel, and today we shall be discussing on alluvial channel. And of course, we started discussion on alluvial channel earlier, and on alluvial channel our main criteria, the design criteria is the concept of critical velocity that we did discuss in the last class. The critical velocity we mean here, it is the non-silting, non-scouring velocity. That means, we need to have a velocity, we need to have our size of the channel in such a way that the dimension of the canal should be such that the flow velocity will be of the type that it will neither cause scouring of the channel nor it will allow deposition of the silt that is flowing through the canal. And that sort of velocity, achieving that sort of velocity is of course very difficult, that we discussed in detail in the last class, but still people are trying. And then the person who tried this design first is the Kennedy, and then he was doing this by observing several stable channel in the region of Upper Bari Doab, which is located in Punjab. Of course, Punjab means now it is in Pakistan, in that part, and then by observing some stable channel he gave it, and then of course, then this theory had lot of limitation, and then Lacey's theories came up, and that way we are now working on alluvial channel. Of course, nowadays then all this say formula like Kennedy's formula, Lacey's formula, all these are basically empirical formula that is based on observed data. These were derived based on observed data, and but after that people started working on possibility of having some analytical solution, or at least to have some analytical basis, although the things may be designed or some parameter may be coming up from some observed value, but still that there should be some analytical basis. That way some semi-analytical approach can be adopted, and say tractive force method is one of such methods. So, we will be discussing all those. Well, let us just start with some of those important issues of Kennedy's silt theory that we did discuss in the last class, but still we will be just starting from that aspect. So, you can concentrate on the slide because we will be showing the formula here basically, that it gave this theory, he gave this theory based on his observation of several stable reach, I am underlining this one, several stable reach of Upper Bari Doab canal system of Punjab and now in Pakistan. That he measured the flow velocity. Actually, after getting those stable reach, he measured the flow velocity and he named this as V0. So, this V0 he measured, and of course, he considered that this V0 velocity will be having a relationship with the depth of flow. That means, if the flow velocity and depth we observe, then we find that the stable remain the channel remains stable for a velocity, and at that velocity if the depth is having a particular value. So, that way he tried to relate this depth and the velocity, and at that point he considered that the width of the channel has nothing to do with this relation, and then relating this V0 and the depth d, he plotted this data in a curve, and then after plotting these things he derived this particular relation, that is V0, velocity V0 is equal to 0.55, then d means depth to the power 0.64. Means suppose if we plot the V0 in this direction, I am just giving one example, say V0 for all those stable channels, suppose several stable channels are there in the upper body drop canal portion, then he observed, then he found that some D0 he is measuring depth, and then at the same time for that particular portion what is the flow velocity that he is observing. And for several years that he found that for several years this particular channel is stable, and that is why he took those channel portion, and then say putting this V0 and this D, say he is getting a curve like this. Well, exactly what sort of curve he got, that is not a question here, but suppose he got several points, and say for example I am giving, suppose the points can be plotted like this, and the equation of this particular curve may give us one relation or equation. So, that equation is say this one, V0 is equal to 0.5 d to the power 0.64, where this V0 is in meter per second, this V0 is in meter per second and d is in meter. Okay. So, this was the popular and famous formula of Kennedy, and then he, as I said, that he did not consider the effect of this width of the channel on critical velocity. And then in fact, to introduce the effect of sill size, here as you can observe in this formula, this velocity, he is saying that this velocity is the critical velocity where no erosion, no deposition will take place, and this depth is only the parameter on which he is deriving this velocity. But from our general concept, we know one thing, that at a particular velocity whether there will be erosion or whether there will be deposition, that will definitely depend on the silt size. If the bed material that is consisting of very fine silt, then at a very low velocity also this can be eroded. If it is suppose a larger size silt, then it may not be eroded. So, that way the silt will definitely have some influence on the entire relationship, and when he initially observed, he did not consider those effect of silt, because the very reason is that he was observing this value only in the region that is the upper body drop canal system, and for that canal system the sediment size or the silt size of the canal are same, identical in all the channel which he considered, these were same. So, what he observed, that he got the same value, he got that okay, this relation is valid, but if we put a different kind of silt, then definitely the relation what he obtained will not be valid, and that he could realize later when this formula was attempted applying in different area having different silt grade. By silt grade we are meaning say silt size, what is the proportion of silt size in a particular silt sample, and say what is the average size, say we call it as the D50 average size. So, that way this effect came later, and so to introduce the effect of silt size, later he introduced a factor m, and this factor is called critical velocity ratio. He named this as critical velocity ratio. So, what this ratio is, critical velocity ratio, that if we see that this m was introduced, which is called critical velocity ratio. Well, so m means it is v by V0. Now, what this V0? So, V0 is the velocity or critical velocity, say we can write it as critical velocity of upper body drop channel region, critical velocity of upper body drop canal region, canal system, upper body drop canal system, and then this V is the critical velocity somewhere else, means the place under consideration, Okay. By this what we mean, that say if we know the critical velocity for the upper Barry-Dwarf canal region, then we can find the critical velocity in other place. Or indirectly, if we know the m value, for a particular region or a particular type of sediment, then we can find the critical velocity for that particular place. So, when m is greater than 1, then it is greater than 1 for silt coarser than the upper Barry-Dwarf canal region. So, that means for suppose upper Barry-Dwarf canal region we have a V0 value, then if the silt size for a different region is greater than or the size is larger than the upper Barry-Dwarf channel region, then definitely the critical velocity will be larger. It will be say erosion, that means the larger velocity will be required for eroding the channel. So, that way it will be larger, and that is why this m value will be greater than 1. And if your silt is finer than the upper Barry-Dwarf canal region, then this m value will be smaller. And so, then people are investigating and different other followers are working on that line, and they have given some value for m also for different part of the country. And then definitely for using this equation, we should not use directly in a particular region. Once we are sure about this m value, say this equation was developed in the region of Punjab. Now, if we want to, which is on the say western part of our country, and then if we try to apply that equation in the suppose eastern part of the country, then we should conduct some experiment, then only we will be knowing that okay, this will be the m value for this particular region, and then only we should apply this formula. Of course, this Kennedy's formula has some of the limitation. And then what is the procedure, how we basically use Kennedy formula for designing our canal? Well, so the basic equation that are used for design are continuity equation that will be required. That means along with the Kennedy's equation, we will be requiring some of the fundamental equation for design of the canal. And continuity equation, as we know, that this is equal to Q is equal to A into V. And then we should use the uniform flow equation, because this canal we design for uniform flow condition always. And so uniform flow equation, again there are several uniform flow equation, as we know, that Manning's equation, Chayes' equation, then Cutter's equation, Bazin's equation, different equations are there. And now while designing this canal, people generally prefer the Cutter's equation. They use the Cutter's equation. Well, but of course, we can try with Manning's equation also. Basically, this we need one relationship, that is to know that, so that we can express V in terms of the other parameter, say R, that is hydraulic radius, roughness parameter, say now I am writing as 1 by n, and the slope, and based on all those parameter, okay, if I write Manning's equation, it will be 2 by 3 s to the power half. So, as B, and R is the ratio of area by perimeter, as we all know, and that means R is a function of what is your B value, what is your Y value, that means what is your width and what is our depth. So, based on that we can express the velocity. So, this is one relation that we know. And then of course, our main equation for design of the canal, that is the Kennedy's equation, that will be required, that is V0, as we are writing this one, is equal to 0.55 m and d to the power 0.64, and this is in metric unit, that is the d is in meter, V0 is in meter per second. Well, but in this entire computational process for designing the channel, there is no mention about the slope. That means, if we do it, if we calculate our size of the canal, here we are not considering the bed slope, particularly when we are using the Kennedy's equation, we are finding that this is the V0 if we assume a depth d, and then we are calculating the critical velocity. Then once we get the critical velocity, we can get the area of the canal. Then from the area of the canal, area is again a function of b and y. So, y means the depth I am talking about, and here of course, we are using the symbol d. So, in this place also I can write d in place of y. Okay. So, depth. So, depth is already known. So, b we can calculate, and then calculating the b. So, once we get d and b, then using this d and b we can calculate r. Then of course, the bed slope will be known to us. Bed slope will be known to us. So, for that bed slope, we can now calculate our uniform flow velocity v. We can use Cutter's equation also, as it is very lengthy. I am just writing the Manning's equation here. V we can use. Now, so for our requirement is concerned that we are considering this is to be critical velocity, but when we calculate by using uniform flow formula, after getting b and d from this continuity equation and this Kennedy's equation, we will be getting another uniform flow velocity. But if these two velocity are not matching, that means our design is not correct. We are considering something to be critical velocity, but in reality we are getting something else, because the flow velocity what we are getting by using uniform flow formula is actually the velocity what we will be getting in the field. So, it is not matching. That means the d what we assume, initially we assume a d value, or rather we take a trial value of d. So, the trial value of d that we did take is not correct. So, what we will have to do? We will have to change the d value. Well, that means for that d value, we are not arriving into a position that our uniform flow for velocity what we are getting is not matching with the, or it is not becoming the critical velocity. So, that d will not serve our purpose. So, we will take another d, and then we will again calculate our V0, and then with that V we will be finding area, then again we will be getting B and D, that is the depth and width, and we are again trying what actually we are getting in the field by using the uniform flow formula. So, that trial and error procedure is required here, and once we find that both the V is matching, then we are getting that yes, our the channel what we are proposing, the design what we are suggesting for B and D are of course acceptable. So, that is what the basic procedure is, but in this formula we are not talking about anything about the slope in the Kennedy's formula. And then later, and of course, we are calculating the B and D based on the continuity equation. Then later Kennedy he realized that no, there is a need of putting some relationship or some proportion of B also, because when he is equating, when he is trying to find this critical velocity with respect to D, then at the same time he found that a B by D ratio can be given. B by D ratio can be given, that if this is the D, then this should be the B, then only the channel will become say stable. So, based on that some experimentations were carried out, and so departments of Punjab area at that time also they conducted experiment, and they gave some B by D ratio. Now, what is the advantage of having this B by D ratio? Because earlier also we could calculate our ultimate size of the channel, because which match with this V, that is the Kennedy's velocity and the uniform flow velocity. So, that we could do, but as it was stated, I have also mentioned that slope was not considered at that point. We are considering a slope which we are getting from the natural terrain, that is from the topography of the channel, rather topography of the area. We are considering that okay, this is the slope we can provide, but always there remain a scope of adjusting the slope to some extent. That is, I was explaining that part earlier also. Say, well, let me take some space. Say this is the area, and they are supposed to carry the water from this point to that point, say point A to point B. We want to construct a canal. Now, we can make the canal, suppose we are starting digging here, and then we can make the canal like this, or one can feel that no, he will go like this, he will go like this, and then another may think that okay, we will do some, then in this case he is cutting this much, depositing this much. In this case he is cutting here lot, but no deposition, and he is going like that. So, that there is a scope of adjusting the slope to some extent, and that we cannot achieve when we use this when we do not use rather B by D ratio, then we do not have the scope of adjusting the slope. Now, when we use B by D ratio, then what we can do, we can use this B by D ratio to find, once we can find, we are assuming a D. So, now considering that B by, so from that we are getting a V, and then from the B by D ratio we will be getting a B also, and using that B we can directly put it, using that B, now we can just try to see that if we adjust the slope with that B and D value, can we get this velocity. So, we will try adjusting this as B, and with some adjustment of this as B, we will try that if we can have the, because once we get this, once we assume this D value, then as we have a B by D ratio, so both B and D are with us. Now, putting this B by D, we can get this relation, and then we can try to see that whether we can adjust this value or not. Of course, this Q is our prime requirement, because we are trying to put that much of discharge. So, this Q is equal to A into V will have to be satisfied. Well, so let us see step by step what we should follow. I have explained it briefly, and now in step by step way what we can do, that first we need to assume the depth D. Well, so depth D we are assuming. Then using the Kennedy's method, we are computing the velocity V, that is the critical velocity we are computing. Then we are computing the area from the continuity equation. Well, then from known area and D, that is the depth D, then we need to compute the width B, that is the bed width B. Of course, when we are using this Q and this our shape can be trapezoidal, shape can be rectangular, anything it can be, that we will have to decide. Again, we did discuss about that part also, how we decide the slope, that we will have to do. Well, then next step is that compute flow velocity using uniform flow formula. This uniform flow formula can be Cutter's or Benning's, but basically Cutter's equation is preferred here. Then we should compare the computed velocity with Kennedy's velocity. Computed velocity means this uniform flow formula, what velocity you are getting. Then from this step we should go for iterative procedure. So, adopt iterative procedure and have the correct value of t, so that both the computed velocity by the Kennedy method and by the uniform flow method, that become almost equal. Of course, we can go for almost equal, exact value may not be matching. So, this is what the procedure is, and if B by D ratio is given, one can adjust the slope to have commensurate value of velocity. So, commensurate value of velocity means again these two velocity should be almost equal. So, that is what the steps that we follow in Kennedy's theory. Well, after Kennedy's theory, the next theory that came is Lacey's regime theory. We just gave the name earlier in the last class, and then we discussed the originally when it was developed and all those things. So, we are not going to that part, but his principle is the regime channel. His principle is the regime channel. I mean, of course, it is similar to having a critical velocity, but what he is suggesting that for a particular size of the channel can be regarded to be in regime condition. And naturally, if we allow, what is regime condition? The naturally, if we allow the water to flow in a channel, then depending on the flow velocity and the size of the channel, it may happen that if it has the erosive power, the water will have erosive power if the flow velocity is high, then it will start eroding the channel. In alluvial channel I am talking about. so it will start eroding the channel. And just the reverse, if we think that if it is the size of the channel is very large and the flow velocity is very low as such, that means we are talking always about all this fact when we are talking about a particular discharge. So, for that discharge, if our flow velocity is very less, then as it will be carrying some sediment with it, because it is in alluvial channel. So, sediment is a must, I mean sediment will have to flow through the water. So, that is why then those sediment will start depositing in the bed, and then so ultimately what we can see that if we allow a channel to run for a long time, it will adjust its own size. The width may increase, the depth may increase, or say due to sedimentation width may decrease and depth may decrease. So, that process will continue, and after continuing this process for a very long period, it will come to a stage that it will not change its width or depth further, and that condition is referred as say regime condition. That condition is basically referred as regime condition. Well, so as a definition of regime condition, we can state like that: alluvial channel carrying a certain discharge, and that part is very important, that when we are talking that this channel is in regime condition, we are always talking about that it is in a regime condition for this particular discharge. That is very important. So, it is carrying a certain discharge, alluvial channel carrying a certain discharge undergoes changes in bed width, depth and slope. Of course, in when I was saying, I was not mentioning about the slope. The slope will also get adjusted when the charge is, when the velocity is more, it will be eroding and slope may that way get increased. When the charge is for that particular discharge, when velocity is less, sedimentation will be there, and if the sedimentation start from downstream, then discharge slope can reduce. Of course, if the sedimentation take place at the upstream itself, then downstream is, so all sediments are getting deposited at the upstream. Then when all sediments are depositing at the upstream and downstream is getting free of sediment, then again that water may start eroding, and that way slope can increase also. So, that way this change of slope will continue. So, this slope is also getting adjusted, and until an equilibrium is reached. So, finally, it will reach an equilibrium, until an equilibrium is reached and become a stable channel, and that stable channel is called, that channel is in regime condition. Well, and for using Lacey's theory, or say before going to Lacey's theory, some of the terms we should have very clear idea. That is, we say that Lacey's principle will give us one channel which will be in regime condition, but what is regime condition we have explained, but then we should know what is true regime condition. So, understanding following terms are important. That is, first let us see what we mean by true regime condition, because many a time we say that this is in regime condition, but true regime conditions are very special, and of course, we must know that in practical field getting a true regime condition is very difficult, but still we go with that assumption. Now, for true regime condition, discharge is constant. Now, if we think about a natural channel, then definitely for a region like India, where our rainfall is fluctuating a lot, I mean seasonal variation of rainfall is quite high, and there we cannot imagine of having a fixed discharge through any natural channel. So, though we see that this channel is in regime condition many a time, but it is not exactly true. Of course, there we find that for the dominant discharge, this can be considered to be in regime condition, but when discharge increases, again a channel may get eroded, and again that there may be deposition in the channel. And that is why for the river of India, where the rainfall is more, suppose rainfall is more in the again northeastern part of India, if we talk about where rainfall is very high, then in those area the discharge is fluctuating a lot, and that is why the channel to have a perfect regime condition is not possible. It always keep on changing, and that is why we are getting braided channel, then channel meandering is taking place, channel, because at some point the sediment get deposited at certain point, and in other part it is getting, in another season it is getting eroded. So, that sort of things keeps on going. But when we talk about man-made channel, because when we are talking about design of channel, we are basically talking about man-made channel. Then suppose man-made channel means it can be irrigation canal. If it is a irrigation canal, then of course we can think to some extent about a constant discharge. If we feel that for the irrigation we will be supplying a constant discharge, but again here also that point comes, because if our agricultural field is in a region like India, this will require irrigation only when it is not raining or when the crop is facing water stress. So, we are not always allowing the same amount of water to the canal, because again if it is controlled by a reservoir on upstream, we need to store water when the rain is coming, and then we need to release water when there will be lean period, and that is why we cannot afford to have constant discharge, but still there can be the variation we can minimize, and we can think of having some constant discharge. And of course, if the canal that we are designing is a drainage canal of a city, then definitely this condition cannot be satisfied, but still we need to design with some assumption in this part, with some discharge considering as the dominant discharge. Then next point is that means for true regime condition this must be satisfied, the first point. Then silt grade and silt charge are constant. Well, what we mean by silt grade and silt charge? Silt grade means the size and distribution of the silt size, rather. Say sometimes we call well graded silt, sometimes we call poorly graded silt or uniformly graded silt. Means poorly, if in a silt portion if we find that all silt are of uniform size, then it is uniformly graded silt. And when it is uniformly graded silt means all are of almost uniform size, this is not good, rather it is bad, because if we have say smaller size, bigger size, then all will get, say smaller size particle will go inside the bigger size particle, like that. Say these are bigger size and then these are suppose some smaller size. So, this smaller size will go inside and then the interlocking will be better. So, but if it is a poorly graded, that is why if it is a uniformly graded, all are of the same size, then there will be lot of gap in between, and that is why these are called poorly graded. So, and well graded means when there are smaller and bigger mix different size. So, like that, this is basically the gradation of the silt, we call like that, but to represent this we need a value. So, generally the average particle size is given to use the gradation, and in this case of course when we talk about grade, our emphasis is to see that whether if the silt are of bigger size, then it will not be eroded easily. If they are of smaller size, it will be eroded easily. Of course, if it become very fine, then of course it is not coming under alluvial formation. Then if it become clay, that is not erodable, that is a different thing. Its adhesive property or its cohesive property is very strong, and that creates some other sort of bonding. But when we are talking about alluvial formation, then if the silt is of finer size, it will be eroded quickly. And so, the average size of the particle is significant, and that is why this by silt grade we mean that what is the size of the silt, and that can be represented as D50, means that if we use sieve analysis and then suppose we are sieving the entire silt and then we are finding that how much percentage of the silt is passing through the 50% of this is finer than that say particular size, and then that we refer as that particular size we refer as D50, that is 50% of the silt will be finer than that particular size, or when 50% is finer, definitely 50% will be coarser than that. So, that particular definition we use for representing the silt size. And then what is silt charge? Well, silt charge means the volume of silt that is coming into this channel. And then suppose not only the size of the particle, what is the total silt concentration, sediment concentration in the water. So, sediment concentration which is flowing means it can be in the suspended form, it may be moving through the bed. So, how much total sediment over the bed, as we were discussing that part earlier also, that is the bed load and suspended load. So, that way what is our I mean say when we were discussing mobile boundary channel, I recall. So, when we were discussing mobile boundary channel, then this part we were discussing uniform flow in mobile boundary channel. So, in that case we were discussing that sediment can be moving along the bed by jumping or rolling, or it can move in getting mixed up with the water. So, entire things total concentration of bed load and suspended load we call as a silt charge. So, how much silt charge is coming, that is important. But the point is that in Kennedy's theory or in Lacey's theory, we are not using any parameter to take care of this silt charge. We are just considering that it will be in regime condition, that when silt charge that is flowing through the channel and the silt grade is constant. Well, then next point, this is more important, that flow occurs in an incoherent alluvial, that is cohesiveness is less, incoherent alluvial, that is it is a alluvial soil, incoherent alluvial of unlimited extent carrying silt grade same as that of the formation. So, this sentence what it means, that for true regime condition, to have true regime condition, our channel should be of infinite extent, that means infinite extent of incoherent alluvium is there, and through that our channel is moving, and then it is carrying silt grade same as that of the formation. So, in the bed through which the channel is going, the suppose through a particular alluvium the channel is moving. So, the sediment size of the alluvium, silt size of that alluvium we will be getting some value. If we take some sample and if we see what is the D50 of that we are getting there. And then what sediment it is coming from upstream, that is coming from far upstream, and that is coming as silt charge. And in that silt charge, the value what we are getting, the dimension or D50 of that what we are getting, there okay, D50 may not be the index, we can use some other index also in case, but whatever index we use, the size of or the grade of silt charge that is coming from the upstream and the grade of silt charge that is remaining in the bed, this must be same, and that entire alluvium should be of infinite extent, and then only we can have true regime condition. Now, when we go into these 3 points and when we think about these 3 points, then one point is very clear, that when we are talking about application of Lacey's theory, then we know that true regime condition, if it is to be achieved, then it is very difficult in the field, and that way there will be definitely some error in the design or limitation of the design. Well, then some other important point when we are talking about artificial channel, that artificial channel there are 2 stages of regime. Well, we are now till this point we are talking about regime condition, then we are talking about true regime condition, what are the conditions that we should have. But in artificial channel, when we are making an artificial channel, then there are 2 stages of regime. So, this is called 2 stages of regime. One is called initial regime and the other is called final regime. And of course, some more points are there that we need to know, but still as a beginner we should know that what we mean by initial regime, when only depth and slope has undergone adjustment. So, initially when water will be flowing through a channel, then the depth of the channel and the width of the channel, finally the width will also get adjusted, but initially the depth of the channel will be adjusted, means if the velocity is high, it will be scouring in the in the depth wise direction. So, depth will be adjusted and the slope of the bed will also be adjusted well. So, initially the depth and slope get adjusted, and when these two are getting adjusted and we are getting more or less a stable channel for some intermediate period, and this is called initial regime condition. And then of course, after some time it will start eroding from the side, and then its width will start increasing, or if it may get decrease also if deposition start, means width will start adjusting. So, when both when this three parameter, that is depth, slope and width, gets finally adjusted, then this is called final regime condition. So, once we get initial regime, then we call this as a final regime condition when width has also undergone adjustment. And in the entire process, the side slope is also getting adjusted. Side slope is also getting adjusted. When we are talking about a regime condition, we say that side slope will have its own value based on the erosion and deposition. So, that way we are not providing a side slope directly here, that we will assume that for the regime channel this is the side slope. Of course, in Kennedy's theory we were not talking about the side slope, and based on the sediment characteristic we can have some side slope there, but here we are saying that in Lacey's theory side slope will get adjusted. In fact, he suggested some value for the side slope, or from observation it can be taken that side slope can be taken as 0.5:1, that is for one depth 0.5 width. So, that way the side slope can be considered. But one more important point that I am putting in red here is, you can concentrate on the slide, that it is not necessary that to reach the final regime the channel will have to pass through initial regime. So, the channel need not pass through initial regime to reach the final regime in all cases. Normally, of course, normally it goes first to initial regime, then it achieves its final regime. But sometimes without passing through the initial regime, it can reach its final regime. For example, suppose final regime width of the channel should be say 5 meter for example, and we have made a 6 meter wide channel, and then the flow is flowing through that. So, what will happen? The depth wise it is adjusting, and then width is also getting deposited, channel sediment that is carried by the channel may be depositing on the side because width is larger, and that way by depositing finally it is coming to the width of 5 meter, which should be in the regime condition, and that way we may get a regime channel without passing through the initial adjustment of only bed and slope. So, that way this is not the necessary criteria. And then more importantly, Lacey's theory, what he studied, and based on his study what are the formula he has given, those are applicable for final regime condition. So, once we are designing a channel, we should know that this channel we are basically designing considering that this is the final regime size, and so those formula will be giving us this value. Well, then he gave series of formula. Initially, of course, he gave 4 formula. These are the 4 formula that were given by Lacey. First is that this is not exactly a formula, that it was found or it was rather observed in many cases that side slope it can be considered as 0.5:1 for when we are designing by Lacey's formula, because side slope we can put like that. And of course, the next formula or the other this 4 formula what he gave is that unlike Kennedy's formula where the silt factor was not given at all importance, later on only they introduced a term called M, the critical velocity ratio, which was used to take care about the silt factor. But unlike that, Lacey first gave the formula for silt factor. Silt factor F, he gave this formula as 1.76 root over MR, where this MR, that is which is basically representing the particle size, and that MR is considered as D50, that MR is considered as D50. So, for the design of Lacey's channel or Lacey's theory, application of Lacey's theory, if we go to the field, first we should collect the sample that through which the channel will be made. Then after collecting the sample, we should carry out sieve analysis, and then after carrying this sieve analysis, then we should see that the size of the sieve through which 50% finer we are getting, that we should consider as the D50, and that D50 value we should put here, and then that we should consider as a representative value of silt factor F. Otherwise, silt will be of different size definitely, and we need a definite value. So, that definite value we are getting by this approach. Well, then we should calculate the mean velocity, and then he gave some relationship between, in fact, he gave 4 relationship. One relationship is between the mean velocity V and this R. R is nothing but hydraulic radius, and that is what this A by P, R is equal to A by P. Well, we know that in Manning's formula or in our uniform flow formula also, we relate this velocity to the hydraulic radius R, and then we take care of the slope. And here this is the velocity which we try to achieve, and then this velocity is equal to, is given as 2 by 5, rather root over 2 by 5 F R. Again, silt factor is playing a role here. And in fact, in all those formula, in most of the formula that he has given, the silt factor has a vital role. So, the determination of the silt factor is very important. Well, and then the V we can have 2 by 5 F into R to the power half. So, that relation he gave. Then he gave another relation. So, here also one relation for V, and another relation he gave between the area, that is the cross sectional area of flow, and the velocity V, cross sectional area of flow and the velocity V. So, between these velocity V and cross sectional area A, he again gave this relationship that A and F square, again the silt factor is coming here, is equal to 140 into V to the power 5, 140 into V to the power 5. Well, now say this you can see very well, just okay, I will show you later. This is one relationship. Then say another relationship he gave, that is the flow equation. Normally in Kennedy's formula or in our design of uniform flow channel also, we were using the say uniform flow equation, that is V is equal to say 1 by n R to the power 2 by 3 and S to the power half. This is the Manning's formula. And there we took that n value that can take different value based on the material, and when we are going into the field and we are seeing the material, then what will be the n value, taking a decision about that is very difficult, of course, unless we have a lot of experience on seeing different type of material and then experiencing how the depth of flow will be, or whether the depth of flow, the uniform flow depth we can have by using a particular numerical value for this n. But here in Lacey's formula, rather than giving 1 by n, the other part is remaining same, say R to the power 2 by 3 S to the power half. This part is remaining same as the Manning's formula, but he gave a value 10.8. By experimenting, by collecting data from different sources, from several portion he collected data, several table section he observed and collected data, and he gave this formula that the velocity can be computed by using this direct formula, where we did not be worried for the n value, rather we can take a definite value of 10.8. So, that way when we try to compute this, computation become easy, but of course, the limitations, those are there, as we are considering a definite value, that is having definitely some limitation. And of course, this formula was not given directly, and but still for freeboard in Lacey's formula we can use this relation. It is actually not for the channel design, but what he gave, that if the channel need to carry higher discharge, freeboard means, say if we have a channel like this, then say by design we are getting that this much is the depth D, and this is the width P. So, we have got this design, but the channel when we are putting in field, we cannot put exactly equal to D, because due to many reasons this depth can increase beyond that, or maybe the wave are coming through this channel, and that way also it can exceed this limit. So, always it is necessary to provide a freeboard. Suppose channel we are constructing up to this much, our water depth is here, but we are always providing a freeboard, and he suggested that this freeboard should be more when discharge is more, and that way he gave a relationship, that is 0.2 plus 0.5 q to the power 1 by 3. So, that relationship was given by him, and now just we want to discuss about this formula another aspect, that is a f square is equal to suppose 140 v to the power 5. See, this formula if we multiply by v, then what we will be getting? Suppose if we multiply by v, then what, sorry, multiplied by v, right, multiplied by v, then it will become area into velocity, and from the continuity condition we know that continuity relation, we know that area into velocity is nothing but q. And for design of channel, always, well, in all this formula we are not talking about q except the freeboard, but in all this formula we are not talking about q, but channel we need to design for a given discharge, and as such we should be careful about, or we should be concerned about what the q value is. So, you can concentrate on the slide that if we write here q, just multiplying by v, this formula will become q f square, and this is equal to 140 and v to the power 6. Now, from this relation, just by multiplying v, we can have another equation which is relating q and v. So, now we can write as v is equal to say q f square by 140 to the power 1 by 6. So, that way we can write v is equal to say q f square by 140 into 1 by 6. So, this way that means from one formula, suppose we want to say q is given, then say in practical field, as I have already explained, that taking the silt data we can find the f. Our target is to design the channel for a particular discharge. So, this q is obtained, f is known, rather q is our required things, it is given, f we have obtained, then we can find what should be the velocity, then this v we can find out q f square by 140 to the power 16. So, this equation can be manipulated to have different relationship, and then we can try to see if this v is to be achieved, and say v is equal to, from this formula we can see what will be the relationship between a and b, between v and y, because r is a function of b and y. From here we are getting some value, okay, and then here we are, or we can go by other way also. So, here it is r, and if we put r here, again slope term is here, and what will be the slope we should take, or say once we get the v value, then we can go back to this formula, say first formula, this one. In this formula, as we have got the v, we put the v here, by putting the v here we can get what the value of r is, because f is already known. Getting that r, we can now put here r and we can get what slope should be, or that way we can indirectly calculate the advisable slope in that channel. In fact, in some channel, suppose of course we say that natural terrain will govern the flow, but we have a scope of adjusting the slope also in some case. Suppose our terrain is having a particular slope, but if we try to increase the slope, we can align the slope in a curvilinear way like this, and then we can have a slope, a different slope. So, like that we can adjust it to some extent. So, what I want to emphasize from this point, that by manipulating these equation, we can have some derived equation which were perhaps were not given by Lacey, but we can derive some relation from this equation itself, and one of those equations are some of those equations are very important and we can directly use. One is the perimeter P. So, as I have already explained that we can have from here, say we are getting Q, and then perimeter is equal to say r is equal to area by perimeter that we are getting, and area we can calculate from this continuity equation also knowing the V, and putting those value we can then indirectly calculate P also. So, P in terms of Q we can calculate, and that formula is 4.75 root over Q. Well, so if Q is given or Q is our required things, from there we can calculate the perimeter, and this perimeter in many a time is used for considering, suppose in a breeze we are considering and we want to reduce the waterway because the breeze will be smaller than the actual width of the river, we narrow down the breeze portion for economic purpose. Then P will indicate what should be the minimum width of the breeze, otherwise our perimeter will further reduce and then it will not be in a regime condition in nature. So, to have the channel in a regime condition or to not to violate the regime condition in a much way, this P is used for that purpose also, finding the minimum say waterway in breeze, and different purpose also used. Similarly, the score depth, this is also used for design of many hydraulic structure, that what will be the R. That R means we are calculating by indirectly from this formula, that is Q, F, and these are coming. This is in terms of total discharge, this is in terms of unit discharge, and by using these things we are getting R, because this is in regime condition. This will be, suppose in a channel we are having this much of depth, but we know that it will get eroded and then it will be depositing, it may deposit or it may erode. If the depth is less, suppose it will be flowing in this depth, then suppose its regime condition depth is much higher, then it will be eroding and the ultimate depth may come up to this portion. And then if we are constructing a hydraulic structure here, then if this water eroded up to this much depth, this hydraulic structure will not remain, it will be washed away. So, we will have to provide some provision, say we are putting some barrier here, so that this erosion, even if it comes to this much of depth, it will not take this hydraulic structure away, and this is called cut-off sort of things. And for designing those things we use this score depth, that is why it is called scour depth, because this is the depth in regime condition, and of course, this is the normal scour depth, but in again depending on some other criteria, if there is band, if it is straight, then we need to, for design purpose, we need to take some safeguard. So, we get the actual score depth, we can multiply it by some factor. And similarly, bed slope we can calculate using this friction factor, seal factor and this discharge. And of course, by two different ways if we calculate, we get two different formula, and these two different formula will of course not give identical value. One is relating R, one is relating Q, but both the way we can go and it will give us some tentative value for this Q for this bed slope. So, all these formula we can apply for design of channel by using Lacey's formula. Well, and as discussed, there are some limitation, and practical knowledge of the practical field of a particular region is very important to apply this equation in a more confident way. Then some other methods are there, as we explained, say tractive force method, and those we will be discussing in our next class. Thank you very much.